Hi, welcome to Quantum Field Theory Lecture 10. Today we're talking about the theorem of Wick's theorem, and it's a helpful tool to compute amplitudes, amplitudes in QFT. We have learned that the so-called scattering matrix can be presented in a very nice and compact form with its exponential of the integral over the Lagrange of the interaction Lagrangian density. It looks really good, however, in this form it is mostly entirely useless. So what we want to do is to expand this exponential for the case that the interaction is actually small, it presents a small perturbation on top of free motion. We want to expand the exponential and then evaluate the amplitudes order by order in between final and initial states, and they will have the form of a power series of insertions of the interaction Lagrangian that is also time ordered. Now, it is very helpful to prove a couple of technical points before. In particular, let's have a look at the simplest form of the Wick theorem, where we can just recover the standard propagator from QFT that we saw before. Let us start with decomposing phi, the field operator, in fields of positive frequency mode fields and negative frequency mode fields. And it has to do this plus and minus sign goes back to a notation by Heisenberg and Pauli that related to this phase, in the exponential function here in the mode decomposition, the positive frequency mode oscillates with a positive frequency by wave mechanics definition, and the negative frequency field oscillates with a negative frequency by wave mechanics definition. Now, what we have to remember is that the most important property is that the positive frequency solutions have the annihilation operators in them, and the negative frequency solutions have the creation operators in them. That's their important property. Now we can look at the following product of fields, phi times x, phi x times phi y, time ordered. That means that y precedes x time-wise. And then we have to consider the two different cases. One where the actual x naught, so the time component of x is actually larger than y, and then we can the time ordered product is just the usual product, phi x times phi y, right? Because x naught is larger than y naught, so y happens before x. So that's why we can just replace the time ordering is just the product of the fields. Well, now we can just insert this decomposition from above and then multiply out all the components. And what is now important, remember the definition of normal ordering. Normal ordering means that if you have products of creation and annihilation operators, that the annihilation operators always sit to the right of the creation operators. That means that if we have products that contain both plus and minus fields, we always want to have the plus fields to the right. This is true for all of the products here, except for this one. So we have to swap the order of the fields here and insert a commutator, and then we get the normal ordered product plus the commutator phi minus x, phi plus y. And in the previous lecture, we have shown that this is just equal to the propagator if y precedes x, right? So then we actually have a neat identity or a neat equation that the time ordered product of phi x times phi y equals the normal ordered product phi x times phi y plus the propagator from y to x. However, we have only proven that for x not bigger y not, but still it's very easy to do the same game here, to start with a case where x naught is smaller y naught, and then the time ordered product is just phi y times phi x, just swaps the order of fields. Then doing the same mechanics leaves us with the same expression that we will get the normal ordered product plus the propagator from x to y instead of y to x. So combining this, we can write that the time ordered product of phi and x times phi y equals the normal ordered product phi x times phi y plus the Feynman propagator. And that's the result of the of this derivation, and it's the simplest form of the Wick theorem. And in a shorthand notation, this is usually called a contraction. So if we have two fields, phi x, phi y, you can write a bracket, or sometimes the bracket is more angular in some books, and this is equal to the Feynman propagator. And in the realistic case of an amplitude, where we have initial and final states, the normal ordered products of fields will just disappear. We are just left with this. After the contraction of two fields, we'll just get a propagator, which is only a complex number and can be pulled out of the product of any operators. So it can be pulled out of the amplitude, and then one can evaluate in following steps the other terms in the amplitude. So it's a very helpful tool to evaluate amplitudes in QFT. Now, a quick note for complex scalars, we have the time ordered product of psi x psi dagger y is equal to the normal ordered product of the fields plus the Feynman propagator, very similar to the real field. However, if we look at the contraction, so that means the contraction of this psi x psi dagger y gives you the propagator. However, the contraction of psi x psi y and psi dagger x psi dagger y is just equal to 0. So they vanish. Now the generalization of this is that for any collection of fields, the time ordered product is equal to the normal ordered product of those fields plus the normal ordered product of all possible contractions. So let's have an explicit example to see what it means. For example, the time ordered product of phi 1, 2, 3, 4 is equal to the normal ordered product of phi 1, 2, 3, 4 plus all the combinations where we contract, let's say 1 and 2 here, and 1 and 3 here, and the other part that is not contracted is normal ordered. So we have to do the combinatorics of contracting all the possibilities of two fields. Here we have 6 of them, and then we have also the possibility to contract twice two fields with each other, and there are 3 possibilities to contract. For example, 1 and 2 and 3 and 4 here, and then 1 and 3 and 2 and 4 here, and 1 and 4 and 2 and 3 here, for example, 3 other possibilities. So this is an example of the Wick theorem applied to a product of 4 fields. Now, in the next lecture, we'll introduce Feynman rules and show how actually those slightly technical and tedious computations of amplitudes, even with the help of Wick theorem, can be greatly simplified using a very beautiful graphical technique which was introduced by Richard Feynman, called the Feynman diagram and the technique, and then by use of the Feynman rules we can actually obtain amplitudes. So that's going to be the topic of the next lecture.